Hello everyone, welcome to a new lecture series on deep learning for control. Deep learning is one of the most popular topics in artificial intelligence and machine learning, which deals with deep neural network based modeling. In this lecture series, we will discuss various deep learning architectures such as feedforward neural network, autoencoder, recurrent neural network, transformer, etc., and their applications in data-driven modeling and control. In this first lecture, we give a brief introduction to neural network and deep learning with various numerical examples. Here is the overview of this lecture. We will be starting with a brief introduction to neural network and its components such as artificial neuron and activation function. Then we move on to deep learning, which can be considered as a subfield of neural network. In general, neural network or artificial neural network can be considered as a nonlinear mathematical model, which is one of the most popular models in artificial intelligence and machine learning. We can start by considering the rectifier circuit, which I think most of us are familiar with. Here we have considered a half-wave rectifier as in figure 1, for which the input voltage can be an AC signal as shown in here. And during the positive half cycle, the output will be same as the input. And for negative half cycles, the output will be 0 in ideal case. This is because of the reason that the diode permits current flow in only one direction. And during negative half cycle, the current through the diode or this resistor will be 0, which makes the output voltage as 0. Mathematically, the output of this resistor can be represented as in equation 1, where the output y is equal to 0 if the input or x is negative, and the y is same as the input if the input is positive. Next, we consider a function called rectified linear unit or ReLU, for which the output is same as the rectifier equation which we saw in the last slide. Figure 2 shows the graph of the ReLU function, where we have the output is 0 for negative x and the output is same as the input for positive x. This is a nonlinear curve which can also be called as a piecewise linear curve. And here we have two linear pieces, one is this one and one is this one. And there is one fold where this line gets folded at x equal to 0. This ReLU function is very important in AI and machine learning because it is one of the most popular activation functions in neural networks. Another significance of ReLU is that we can represent any piecewise linear function using ReLU functions. As an example, we can consider a saturation function, which is one of the popular nonlinearity present in practical systems. Saturation normally occurs because of the physical limitations of the system, and it is commonly occurs in electrical motors due to magnetic saturation, which limits the torque or speed of the motor. And also a control valve can get saturated because of mechanical limits and etc. Here we can see that a saturation function can be represented as sum of ReLU functions as in this equation 3, and this figure 3 illustrates this idea. Here we have ReLU of x plus 1 is plotted in red color, where we can see that x plus 1 equal to 0 at x equal to minus 1. And if x is greater than minus 1, x plus 1 is greater than 0. Therefore, the graph of ReLU of x plus 1 will be same as the graph of x plus 1 if x is greater than minus 1. And it will be 0 if x is less than minus 1. Similarly, for ReLU of x minus 1, the plot is shown in green color. And we have x minus 1 equal to 0 at x equal to 1. And for x greater than 1, x minus 1 is greater than 0. Therefore, for x greater than 1, ReLU of x minus 1 will be a line with slope 1. And for x less than 1, ReLU of x minus 1 will be 0. Now, if we subtract this function from this function, we obtain this curve in blue color, where we can see that until this point, this function is 0. Therefore, this output does not get affected. And after this, we will be subtracting this portion from this, which makes the output to go like this. This is the graph of ReLU of x plus 1 minus ReLU of x minus 1. And this function goes from 0 to 2, which we can see here. Now, if we subtract 1 from this function, we obtain saturation function as can be seen in this figure. And this is the equation for saturation function. So the saturation function is also one of the activation function in neural networks. Similarly, we can represent many other piecewise linear functions such as step function, signum function, etc. using a ReLU function. Next, we can see a few more examples using ReLU functions. Here we can see the linear equation y equal to minus x minus 2, for which the graph will be as in this figure A. And we can see that minus x minus 2 will be equal to 0 at x equal to minus 2. Here we can see it from here. And for x greater than minus 2, the output is negative. And for x less than minus 2, the output is positive. Therefore, ReLU of minus x minus 2 having an output of 0 for x greater than minus 2, which we can see here. And for x less than minus 2, the output will be same as this graph. Now we can consider another linear function defined by y equal to 2x minus 4, which is a line with slope 2 and y-intercept minus 4. This function becomes 0 at x equal to 2, which we can see from this graph. And for x less than 2, the output is negative. Therefore, for ReLU of 2x minus 4, when x less than 2, the output is 0. And for x greater than 2, the output will be same as the input. Now we can consider another example, y equal to 5x minus 15. And this function becomes 0 at x equal to 3, which we can observe from this figure. And for x less than 3, the output will be negative. And for x greater than 3, the output will be positive. Therefore, ReLU of 5x minus 15 having an output of 0 for x less than 3. All these functions are piecewise linear function. And here we can see the line is folding at x equal to 3. Now we can combine all these previous examples where figure A and B and C are considering three ReLU functions which we have explained so far. In the fourth case, we just take a weighted sum of these ReLU functions. So we will get the output as shown in this figure. For the first function, we had a fold at x equal to minus 2, which is also appearing here. After that, if we sum this function, we will be having another fold at x equal to 2. After 2, the output of this function will be added here, which resulted in this region. And after 3, we had this kind of a large increase. But here we use a minus 0.6 as the scaling factor. So this term will be subtracted from the output, which resulted in a portion with negative slope. And here each of these individual functions we can consider as an artificial neuron, where this slope or coefficient in the linear term is called as the weight parameter, and the intercept term is called as the bias parameter. Here, these folding points can be adjusted by changing the weight and bias parameters. If we change this weight parameter, the slope of this linear portion will also get affected. On the other hand, changing the bias term shifts the folding point without affecting the slope of the linear piece. Each of these equations we can represent as in this equation 8, where A2, A1 and B1 containing all the coefficients in these equations. For this first equation, A2 will be simply equal to 1, and sigma 1 will be ReLU, A1 will be minus 1, B1 will be minus 2. For the second equation, A2 will be 1 itself, sigma 1 will be ReLU, A1 will be 2, B1 will be minus 4. Now when we comes to this fourth equation, here we have a linear combination of three ReLU functions. So A2 will be a row vector which contains 1, 0.5 and minus 0.6. Sigma 1 will be a vector valued function which contains three ReLU functions. A1 will contain all these weights. It will be a column vector which contains minus 1, 2 and 5. And B1 will be also a column vector which contains all these bias terms, minus 2, minus 4 and minus 15. Here all this part like sigma 1 of A1x plus B1, we can represent it as a function f1 of x. With this final expression we can represent as f2 of f1 of x. This is a popular version of the neural network and it is called shallow neural network, and we can represent it as fnn of x. While training a neural network, our objective is to find the optimal weight and bias parameters so that the resultant curve will fit the data. And with a sufficient number of neurons, this kind of piecewise linear curves can approximate any relationships in the data set with sufficient accuracy. Here we had a function with 3 neurons and we got 3 folds in the line. Now suppose if we have 100 neurons in this equation, we are just taking weighted sum of 100 neurons. We can have at max 100 folds in this line. Let's say if we have million neurons, then we can possibly have million folds. Million folds means this line will be possibly looks like a continuous function. It will be a fair approximation to any continuous function. That's why neural network can able to approximate any complex nonlinear function with a sufficient amount of accuracy. And we will see more about this in the upcoming lectures as well. Next, we move on to a general structure of a neural network. Here we are considering a feed-forward neural network, and it is one of the most popular version of the neural network. A neural network or NN can be represented as a composite function as in equation 9, where we have a composition of L number of functions. Each of these individual function can be considered as a layer of the neural network. And these functions from F1 to FL-1 are called as the hidden layers. And this function is called as the output layer, FL. And we also have an input layer, which is normally the identity function, which simply passes this input. And F0 of X is X itself. So we do not need to include it in this equation. We will be having F1 as the first hidden layer, FL-1 as the last hidden layer, and FL as the output layer. And each of these function can be represented as a composite function itself, as in equation 10. Sigma I will be the activation function, which contain all the activation functions for the ith layer. AI is the weight matrix, which contain all the weight parameters in the ith layer. VI is the bias vector, which contains bias terms for all the neurons in the ith layer. Here VI will be the input to the ith layer. In general, we denote the number of layers, like the number of hidden layer plus output layer, as the depth of the neural network, and it is denoted by the letter L in this lecture series. And the width of the neural network is denoted by the letter W, which is the maximum number of neurons in a layer. Here Mi denotes number of neurons in the ith layer. Now we can briefly discuss artificial neuron, which is the building block of a neural network. And an artificial neuron can be represented as a composite function as in equation 11, for which the example we have already seen with ReLU. Here we have considered a neuron with n number of inputs, where the inputs are like x1, x2 till xn. And inside this neuron, we will be taking a weighted sum of all these input, where this a1, a2, an are all the weighting parameters. After taking a weighted sum, we will add a bias term, which is denoted by this b term. This will be an affine transformation of the input. After that, we will apply a nonlinear function to it. The nonlinear function is denoted by sigma, which is called as the activation function. For example, the ReLU, which we already seen, is a popular activation function. And here we can see that if we have n inputs, then that particular neuron will contain n number of weight parameters, and the bias is scalar. If we have many neurons which take the same input, let's say the same input as this one, so that will form a layer. In that case, this A becomes a matrix, which is obtained by stacking these parameters for each neuron. The artificial neurons are inspired by the biological neurons, which are occurs in our brains. And the biological neurons can be represented as in this figure B, which consists of a cell body and an axon. The cell body part is equivalent to the weighted sum portion of the artificial neuron, and this activation function is inspired by this axon. In the case of biological neurons, these dendrites will collect the inputs from adjacent neurons, and this input will be passed to the cell body, and it will take an aggregate signal based on all the signals received from the dendrites. And this aggregated signal will be sent to the axon. If the aggregated signal is of sufficient magnitude, then axon will say yes, or it will give a positive signal. This biological neuron will be there in our brain, mostly in the parts such as cerebrum and cerebellum. So the cerebrum or the cerebral cortex is the part which deals with the decision-making process. And in the cerebral cortex, we have billions of neurons. The cerebrum deals with tasks such as thinking, reasoning, decision-making, and it also contains the memory. Whereas cerebellum involves tasks such as coordinating movements, balancing, posture control, etc. It is mostly associated with controlling the mechanical actions in the body. Neurons exchange information using electrical and chemical signals. The chemical signals consist of neurotransmitters such as serotonin and dopamine. Neurons also control our emotions. For example, whether we are happy or sad is influenced by the release of chemicals like serotonin and dopamine, and their release are controlled by neurons. Normally, taking good decisions or doing good things can make us happy. This is due to the dopamine that acts as a reward signal which reinforces actions that resulted in good outcomes. And while making decisions, cerebrum considers past experience, memories, emotions, and possible outcomes. This decision-making mechanism can be viewed as a voting system where some of the neurons say yes or generate an excitatory signal, some of the neurons say no or generate an inhibitory signal, and the rest will remain neutral or does not take part in the voting. This idea is inspired in the development of the winner takes all or WTA network model, which is a popular neuroscience model. For example, the Indian cricket player Sanju Samson told in an interview that every time he faces a ball, his mind says to go for a six. Here, the mind says means most of the neuron gives a positive signal or excitatory signal for the thought of hitting a six. Now, while the ball is approaching, if it looks like a Yorker directed at the stumps, the neurons will quickly changes its output and the cerebral cortex quickly changes the decision to defend the ball. These decisions are influenced by the opponent bowler, pitch condition, whether we are batting first or chasing a target, format of the game like whether it is a T20 or a test cricket, etc. Similar situations occurs in other sports as well. For example, while Lionel Messi playing football, the neurons will quickly changes the decision to move the left and right legs to dribble the ball, giving pass to teammates, or shooting for a goal. Here also, the decisions are influenced by the current position in the ground, opponent players' actions, time remaining in the game, etc. And similarly, there can be many other examples such as investing money in the stock market. We have to decide which company's share to buy, how much money to invest, and all these factors. In day-to-day life, we will be having many decisions like whether should we eat ice cream today or should we go for some healthy food. And all these decisions we will make based on some analysis. To summarize, every actions of humans or animals are decided by the biological neurons, whereas in the case of AI, everything AI does or AI will do in the future, artificial neurons are the key factors. Next, we move on to the deep learning, which is a subfield of neural networks. And deep learning uses deep neural network based model. And a deep neural network has more than one hidden layer, which means the depth of the neural network will be greater than 2. We have seen examples of neural networks with one hidden layer or depth is equal to 2. These particular neural networks are called as shallow neural network. And for any neural network with the number of hidden layer greater than 2, we call it as a deep neural network. Deep learning particularly focuses on deep neural network based models only. The initial research in neural network were focused on shallow neural networks. Later on, it is established that adding more layers can enhance the representation capability of NNs, can result in automatic feature extraction and learn hierarchical features, and can lead to better performance in large data sets such as text, image, audio, etc. This resulted in the popularity of deep learning in various applications such as image processing, speech recognition, robotics, autonomous vehicles, healthcare, recommendation systems, etc. In general, a mathematical model is used for describing a system or a problem of interest using various mathematical equations. And the mathematical models can be of different types, such as white box model, which is based on physics-based equations, and the black box model, which are like data-driven models in which the parameters has no physical significance. And deep learning models comes under black box models since its model architecture and parameters doesn't have any physical significance. We can also have gray box model, which are hybrid model that are like combination of white box and black box model. For a gray box model, example can be like a physics informed neural network, which is very popular nowadays. And these models use neural network models, and we will also include physics-based relations for improving the performance of the model. Figure 10 illustrates how this deep learning is related to AI. AI is a broader field which is dealing with the programming a computer so that it can learn from the available data and performs tasks involving intelligence. And machine learning is associated with learning models from data. So it can be any mathematical model. And these models can be used for prediction or identifying trends or patterns in the data, etc. Neural network is one of the most popular subfield of machine learning. It uses neural network based models and can be considered one of the most popular models in AI. And deep learning is a subfield of neural network which focus only on deep neural network models. Based on the type of the data set used for training the model, we can divide deep learning algorithms into supervised learning and unsupervised learning. In the case of supervised learning, we will use labeled data set, which can be represented as in equation 12. x1, x2, xn can be considered as the input vectors, and this y1, y2, yn can be considered as the labels or the output corresponding to this input. So therefore, in the case of supervised learning, we will assume this kind of data set is available and learn some function which can predict the output given the input. And in the case of unsupervised learning, we will use unlabeled data set where the label information is unknown. In many of the practical cases, the label information will be unknown. So all that we know is different variables in the data set, and there is no label associated with it. We have to learn model so which can find trends or like patterns in this data set, and that kind of problem comes under unsupervised learning. And there are other categories as well, like semi-supervised learning and also reinforcement learning. In this lecture series, we will be mainly focusing on these two categories. In general, the mathematical models that we discuss in this lecture series can be divided into static and dynamic models. The static model discusses steady state or time independent relationships amongst variables in the system. So for example, yk is the output at the current instant and it only depends on the input at the current instance. Whereas in the case of dynamic model, the current output will depend on the past output and also input as well. For example, in this equation, this output yk is a function of the previous output yk minus 1 and also the previous input. These kind of models are very popular in control systems because for designing the control action, we need to know how this control action is going to affect the future outputs. As an example, if we consider the HBO series Game of Thrones, the series is all about a number of good and bad decisions, where it started with a bad decision, which was mostly an instantaneous or impulsive decision, and the rest of the series containing events which are consequences of this decision. And the key takeaway message from the series is that a great king is someone who knows the past and present of the people. Here by past, we mean the true history or what is actually happened in the past, like past actions and their consequences. And by present, we means what is actually happening in the other parts of the country. Therefore, if a king knows the past and present of the country, he can use that information to take wise decisions. When it comes to control system, dynamical model captures the past behavior of the system, like the relationships between past actions and their consequences. And the state information like current state captures the present of the system. For knowing the present state, we normally use state estimators or observers. That's why estimators such as Kalman filters are very popular in control systems. Therefore, if we have a dynamical system with the current state information available, we can use it for predicting consequences for future actions, which helps us in taking the best or wise actions. This is the central idea of optimal control algorithms such as linear quadratic regulator and model predictive control. Coming back to the Game of Thrones, a lot of people and critics were not happy with how the series ended, which was considered to be mostly disappointing and unexpected. However, from a control system point of view, we can say that the ending was great. Considering how the story started, this was one of the best ways it could have ended. Coming back to the lecture series, in the rest of the series, we will learn different deep learning algorithms for static and dynamic model identification from data and their applications in control. That leads us to the end of this lecture. Thanks for watching.